Hi folks, and welcome to an OALabs Patreon exclusive tutorial. Today we're going to be talking about emulation. Now we've kind of flipped this tutorial series around, and instead of telling you all the wonderful things about emulation and how you can use emulation, I've decided to start with describing what an emulator is and having you build a simple emulator just to understand the fundamentals. I think once you understand how an emulator works under the hood, the rest of the series where we talk about when you should use emulation and when you shouldn't will be a lot more clear because you'll understand the reasoning behind that. Hey, so if you're seeing this, it's because you're watching this tutorial on YouTube or Twitter, X, I guess now it's called X. So I'm going to take a minute to shill for our Patreon. If you like this tutorial, if you like what you're seeing here, go check it out. There's a lot more like this. We have examples, labs to do that accompany the tutorials, all that good stuff. So if you like this, go check it out. So with that, let's jump in and we'll start talking about how an emulator works under the hood. So the first thing that we need to clear up is that emulation is not the same as virtualization. The two are sometimes used interchangeably when you're reverse engineering, but they serve two different purposes and there are very big distinctions between the two. So for emulation, the key component here is that it's an interpreter. It interprets CPU instructions. It doesn't actually execute those instructions on the CPU. Whereas virtualization, that's actually what it does. It actually executes the assembly code on the CPU, but in a little container. So that's the main difference between the two. And then from there, we follow into a few more differences here. So for emulation, of course, because you're not running the code on the CPU, you can run cross-platform architecture code. So you can emulate, say, an ARM device on an x86 CPU because it's an interpreter. It has nothing to do with the CPU that it's running on. This is how you get things like Game Boy emulators running on your PC or Nintendo emulators running on your PC, right? Those architectures are very different, but you're able to emulate them because you're not actually making use of the CPU. Virtualization, of course, you are executing the target code on the CPU, so you need to have the same architecture on the CPU as the target that you're executing, right? You can't just take an ARM binary and virtualize, run it on an x86 CPU. It's not going to work, right? So that's another fundamental difference is you can have a different architecture between the target and the host for emulation, but for virtualization, they need to be the same. Now, because emulation is an interpreter and it's not executing natively on the CPU, it is way, way slower, exponentially slower than virtualization. Virtualization is close to native speeds if done right. Emulation is much, much slower. Now, we will talk about how some frameworks have gotten around this and sped things up quite a bit, but let's just leave that for right now. The speed difference is astronomical. All right, so the final main difference here is that the security model is very different between virtualization and emulation. For an emulator, your security model is limited to the interpreter. So if you want to break out of the emulator, you need to find a bug in the actual interpreter, the parser of the code. There's no danger of the target executing on your host because it's not actually executing. It's just being read, and I'll show you in a minute, chained through a series of if-else statements. There's nothing really to execute on your host in an emulator. It's very safe and very self-contained. The security model is basically limited to the interpreter. Of course, you could find a bug in the interpreter, but that's not targeting the host itself. There is an exception with JIT, but again, many exceptions with JIT. I'll talk about that in a bit. For virtualization, very different. The security model rests on the virtualization boundaries in the CPU. You're actually executing native code on your CPU. It's just in a container, right? Which is limiting access outside of the container. So the security model is very different. Obviously, virtualization has been around for a really long time, and there's fewer and fewer breakouts. I mean, it's in fact quite rare, and they're quite expensive if you do find an ODE for. But the security model is just different. Okay, so what is an emulator? I stole this from a random person on Wikipedia. I don't even think it was cited on Wikipedia. In its simplest form, CPU emulator is an interpreter. Basically what it is is a virtual representation of a CPU, registers, memory, etc. in code. So like lists, dictionaries, etc. Those are what represent the registers. And each instruction that is interpreted, each CPU instruction, the semantic equivalent of the impact of that instruction on a real CPU is mimicked in the interpreter. So that's basically all it is. Now, again, these things can get quite complex. I'm going to talk about some exceptions in a minute, but at its very core, an emulator is simply a series of if-else statements that take CPU mnemonics and operands and filter them through the if-else statements until they find one that matches, and then perform a semantically equivalent operation inside the interpreter as what would happen on a CPU. It's basically building a CPU in if-else statements. That's what an emulator is. Now let's talk about emulation boundaries. So this is what parts of the code are emulated, how much stuff is emulated. I've broken these down into 3 main boundaries. Obviously, with these tools, as you guys know, the boundaries are kind of gray and some tools overlap. But basically, we have 3 main ones. We have CPU emulation, user mode emulation, and system emulation. And the way that this maps to Windows is if we look at the Windows stack here, a simplified Windows stack, you have your application, which talks to the Windows API, which is just a series of DLLs. Those DLLs use syscalls to interact with the kernel. Inside of the kernel, you have drivers, which interact with the HAL, the hardware abstraction layer. And the hardware abstraction layer is exactly what it sounds like. It is a way for code to interface with the actual hardware of the computer. So the actual CPU, the bus, etc. Right? So that's the Windows stack. Now let's talk about each one of those emulation boundaries and how they map to the stack. So the first one here is the CPU emulation. So CPU emulation only emulates CPU instructions. Sometimes you have a memory manager. You usually have to have a memory manager. But the key component here is you're only emulating CPU instructions, which means it has nothing to do with API calls, nothing to do with the operating system. And in fact, at the CPU emulation layer, Windows looks the same as Linux, looks the same as Mac, etc., right? As long as they're on the same architecture. So an x86 Mac looks the same as an x86 Linux machine, same as x86 Windows, because at the end of the day, the assembly code is the same. We're not talking about doing any sort of calls or anything like that. So what is this good for? Well, it's good for emulating shellcode where there's no calls, good for emulating tiny little blocks, little thunks of code, right? But anytime you have a call that might lead to a Windows API or something like that, you can't emulate it with a CPU emulator, you must fake it. So how does that map to the Windows stack? Well, here you can see an example. The only thing you can really emulate with CPU emulation is just tiny snippets of code, like I've shown you here. You can't really do anything else in the Windows stack, right? So the next mode is user mode emulation. This is where you're emulating the CPU instructions, but you also have an OS-specific API layer. So what do I mean by this? Well, I mean anytime the code, say, makes a call to kernel 32 DLL, your emulator has a fake kernel 32 DLL with fake exports that when they're called, the emulator will mimic what actually happens when you call those API exports in Windows. So this actually is able to emulate an entire user mode process. There's 2 ways that this can be done. We're going to talk a little bit more about that in a minute, but basically you can either emulate at the high level, so this would be the exports for the DLLs, or you can emulate at the kernel level. This would be syscalls. And the emulating of the syscall layer, again, we'll talk about this in a minute, but that has a smaller surface to emulate. So there's a lot less syscalls than there are API exports, right? There's tons and tons of DLLs for Windows, only a limited number of syscalls, but the syscalls are more complex. So you have to handle more within the syscall. Whereas if you emulate at a higher level, at the DLL level, then you have a much larger surface area to cover, but each API is specific to one task, so they're easier to implement. And when we talk about different emulation frameworks, we're going to talk about that difference. But for now, let's just assume that user mode emulation ends at the syscalls. So this means anything inside of the user mode process for Windows you can emulate, and the only thing you have to fake is the syscalls, right? So this is what we consider user mode emulation. Lastly, we get to system emulation, where we actually can emulate an entire operating system. So you can load the operating system inside the emulator. To make this happen, you need to virtualize or emulate hardware, right? Because that's the interaction layer now. The operating system is now going to be talking to a series of hardware that it expects to be present. So you have to emulate that or fake that in your emulator. However, you can run a full OS like this. And just to show you guys what that looks like in the Windows stack, basically the whole OS runs within the emulator, and what you're faking is the hardware. So let's talk about how this maps to actual emulators that you would use, open source emulators. So here we have the breakdown. At the CPU level, we have GHydra's emulator, which many people probably don't know about, but there is a full-fledged emulator inside of GHydra. And also we have Unicorn, which everyone is probably familiar with because Unicorn is the underpinning for most emulation in the malware analysis space. Then at the user mode side, we have Speakeasy, Keeling, Dumpulator. There's many emulators that sit in this space that are open source. I just grabbed 3 of the largest ones, or most used ones, I guess. And I'll talk a little bit more about those when we actually start using the emulation frameworks. There's large differences between them, but basically for right now, you can consider them able to run a user mode process. And then for system emulation, you basically have QEMU and Box, right? So Box comes standard inside of IDA. You can emulate Windows bootloader stuff in Box, etc., etc. QEMU, you can run a full operating system. So anyone who has an M1 Mac, if you've ever tried to run x86 Windows on your M1 Mac and you wondered why it's so slow, it's because it is literally running inside of an emulator called QEMU. So that's basically how it breaks down. For our tutorial series here, we are going to be focusing on CPU emulation and user mode emulation, not system emulation. System emulation is a useful tool if you are trying to do something like a large-scale sandbox or something like that, but you get a lot less control and you need to write a lot more code in order to do instrumentation. So if you're just trying to reverse engineer a binary, it's not as useful. In fact, it's quite useless. It's much better to use a user mode emulator. You get a lot better control, and it's a lot faster to implement stuff if you need it. So that's where we're going to be focusing for the tutorial series. Now, there was one kind of troll here, and that's that basically all these user mode emulators are just Unicorn. So Unicorn is basically the framework that is used underneath all of these. There's a mega troll later on. I'm not going to spoil it for you guys, but remember the slide when we start talking about Unicorn later on. But basically, Speakeasy, Keeling, Dumpulator, they all use Unicorn under the hood. So that's the CPU emulator. And then all these user mode emulators do is add their own flavor of fake Windows APIs on top of Unicorn. Okay, so let's talk a little bit about how an emulator actually works under the hood. And in order to do that, we need to do a quick review of what execution of assembly actually looks like at the CPU level. So I have a very simple example here. We have 2 moves and an add. We move 2 immediates into EAX and EBX, and then we add them together. The result is stored in EAX. And to make things easy to follow here, I've also written out the hex bytes that map to these instructions in orange here. So what does this actually look like when you execute it? Well, on our first step here, we move 2 into EAX. So you can see the EAX register now has 2, and EIP has incremented the size of the instruction, right? It's important to remember that when you're writing an emulator, you must account for all impact of an instruction on the CPU. I'm going to talk a little bit more about why that's difficult in a couple more slides. But for right now, just remember that any sort of impact that you have of an instruction on the CPU, on memory, must be accounted for in your emulator. So we execute the next instruction here. We move 3 into EBX, and EIP has incremented again. Then we add them together. The result is stored in EAX. So EAX now has 5 in it, and EIP has incremented again. So that's just a refresher of how assembly executes the impact on the registers. And now that we know the impact that these instructions have on the CPU registers, let's build a simple emulator. So here we go. We have used the capstone disassembler to disassemble these bytes instruction by instruction. And for each instruction, we've passed them through a series of if statements that check the mnemonic. And once we match the mnemonic, we replicate the CPU behavior on our fake CPU. What is our fake CPU? Well, it's actually just a Python dictionary with register labels for the dictionary entries. So that's actually what a CPU emulator looks like at its most basic form. And just looking at this, hopefully a few things are starting to make a lot more sense, i.e., how could you ever infect yourself with code if this is how it's executing the code? It's not really possible unless you break out of the Python interpreter, right? Other things that might become pretty clear to you is that this is pretty slow. It's a slow way of doing things. In a minute, I'm going to talk a little bit about speed and how it actually compares, but you can immediately see that obviously a bunch of if statements in Python is a lot slower than a CPU instruction, right? And some other things you can see here is that we have only implemented 2 registers in the CPU because it's a lot of code to implement all the registers, and we only need 2 for this code. So if you wanted to replicate an entire CPU, it's going to be pretty complex. You're going to have a lot of registers, you're going to have a lot of if statements, etc., etc. But at its core, this is basically what a CPU emulator looks like. So that brings us to the demo portion here. I'm going to hop over to an editor, and I'm going to show you guys how to use Capstone as a disassembler to build a very simple emulator and emulate some shellcode. So for our demo here, we have set up Capstone, which is a disassembler. There's a Python interface for it. The way it works is you feed it raw bytes, and it disassembles those into the instruction set that you choose for the disassembler. In our case, we are choosing x86 and 32-bit, right? So once we set up the Capstone disassembler for x86 32-bit, we then have a Capstone engine here. We're setting 2 additional settings here, detail true and skip data true. And what these will do is detail tells the disassembler to include extra details about the instruction that it's disassembled. This is important for our use as an emulator. We want additional information, which I'll show you in a minute. And skip data is actually not necessary in this case, but what it does is it skips instructions that can't be disassembled. So if you have data mixed in with your code, it'll skip over the data as best as it can, right? If you don't have that set, the emulator will actually stop as soon as it can't disassemble an instruction. So those are the settings. The example that we're using here is a simple piece of shellcode called add.bin, and it's actually the same shellcode that we showed you a minute ago in the slides. And we're just reading that file in and storing it in code as bytes, right? So that's the first part of our demo here. We're reading that file in and we're setting up the Capstone disassembly engine. Now, before we proceed, let me open that add.bin in IDA, and I'll show you what the contents look like when you open it in IDA. Again, it should be the exact same as what you just saw in the slides, but I'm doing this so that you have the process for when samples get a little bit more complex. So let's pop over to our VM, and you can see the file here is very simple. It's exactly what we saw in the slides. We move 2 into EAX, we move 3 into EBX, and then we add EAX and EBX. So we're back in our notebook. We have our file read in and our engine set up. Now what we need to do is we need to create some registers. Now we know from looking at IDA that only the EAX and EBX registers are used. So if we want to create our simple emulator, we only need 2 registers. And these registers will be used to track the values that are placed in the registers as we emulate this shellcode. We also need an instruction pointer. In x86 32-bit, the instruction pointer is EIP. And of course, the instruction pointer is going to start at the beginning of the code, so its value is going to be 0, offset 0. Now we get to the core of the emulator. The core of the emulator is actually a simple while loop that iterates through the code using EIP as an offset into the shellcode And as long as the offset is not equal to the end of the shellcode, we continue the while loop. So what this will do is this will iterate through the shellcode until we reach the end of it. Now, how do we iterate through it? Well, if we look at the very bottom here, we have an increment for EIP, and we increment not by 1, but by the size of each instruction that is disassembled by the Capstone disassembly engine. Now remember, each instruction is going to have a different size. They can have up to 15 bytes, depending on what the instruction is. So when you're iterating over instructions in an emulator, you need to make sure that you have disassembled the instruction to determine the size, and then skip over that to get to the next instruction. So this is our increment, and this is our halt state for the emulator. Now, once we get into the emulator, so for each instruction, we'll save the address of EIP, and we're only doing that so that we can use that address inside of our code without having to reference this clunky registers notation here. So here is the key to our disassembly emulator. We disassemble the first instruction up to size 15. So we take the code. These are all the instructions that we've been given to emulate. We use the address, so this is where EIP is pointing, the instruction pointer, plus 15 bytes to choose the maximum size that an instruction can be, and we pass that to our disassembly engine. Now, if we've passed additional bytes, it doesn't really matter. The disassembler will only disassemble the number of bytes required for the instruction. And what's passed back is an instruction object which contains information about the instruction that was just disassembled. So we have things like the mnemonic, that's the actual name of the instruction, and the operands. These are the values that are passed through the instruction. Now, the first thing we do here is we do a nice debug print. We print out the mnemonic and the op string. The op string is basically just all of the operands together in a string. And we print that out to the screen so that we know what's going on, right? Then what we need to do is emulate the instruction. So for our emulator, we have implemented 2 instruction handlers, one for move and one for add. Now, of course, if you're writing a generic emulator and you don't know the shellcode that you're going to be emulating, you would have thousands of instruction handlers. But because we know we only need 2 instructions handled, we just have 2 instruction handlers. Now, each instruction has various types or permutations, depending on the type of operand that is passed to it. Of course, you can move a register to a register, you can move an immediate to a register, you can move a memory address to a register, you can move a register to a memory address. All different combinations of move need to be handled, but in our case, we know that there's only one instruction variation we need to handle, which is moving an immediate into a register. So what do? We check to make sure that the first operand at offset 0, is a register, and operand 2, operand at offset 1, is an immediate. For any other case, we don't handle it, right? Our emulator is very specific to the shellcode that we're analyzing. Once we've established that this is the variant of instruction we want, we grab the immediate value from operand 1, and we place it into our emulator register value at whatever the register is in operand 0, right? So this code right here is actually emulating what would really happen in a CPU. In a CPU, you would have a series of registers, and anytime you found an immediate move into a register, you would take that immediate value and you would place it into the register in the CPU. In our emulator, our registers are just a dictionary of values, and all we have to do is store that immediate in the dictionary. That's the emulator. And this is the core concept behind the example and the labs that you're going to be doing, is that an emulator is truly just a series of if statements that handle each instruction and an instruction variant and replicate in code what happens in a CPU. So the same is done for the add. In this case, we're only handling an add between 2 registers. So add register 1 into register 0. So we have to check for that variant. We check that the first operand is a register, The second operand is a register. And once we've established that, we just add the two registers together and store the value in the first register. And again, in our case, the registers are just a dictionary called registers. So how do you add the values? Well, you index into the first register and index into the second register in the dictionary and store the result in the first register place in the dictionary. And that's pretty much all there is to our emulator. If there's any other instruction, we print an error and halt emulation. So what happens when we actually run this? Well, Shift Enter, you can see at the bottom we already had the result. We have a print statement for each one of the instructions that we handled. And at the end, we're printing what's in our dictionary where EAX is located. And the result is 5. So 2 plus 3 should be 5. We've correctly emulated this code. So there you go. That is a 2-instruction emulator built on top of the Capstone disassembly engine. And again, the core concept here, my doggo's making lots of noise. And again, the core concept here is that our simple Python emulator is conceptually no different from any commercial or open source emulator that you might be using. We have some if statements that check for different instructions and replicate their behavior in code. That's exactly what an emulator does under the hood. All right, I hope you guys enjoyed that. Just a quick reminder, go check out our Patreon. We have a lot more tutorials like this, hundreds of hours of live streams with us reverse engineering, and we have lab exercises that go along with these tutorials if you want to get some hands-on practice. Go check it out. We'll see you in the next tutorial.